Okay, let's have a look at Gay-Lussac's or Amonton's law. So if we look at the relationship between pressure and temperature, so we're assuming we're holding the mass or the number of moles of gas present, and we're also holding the volume of the container that holds that gas present, we can draw a graph with that interaction. So from this graph we see that as the pressure increases, the temperature also increases. This means that we have pressure being proportional to temperature. And we can turn this into an equation, P equals some constant times the temperature. Now if we adapt this equation, we can actually divide both sides by T so that we get pressure divided by temperature, and we set up an initial set of conditions that is equal to our constant. We can also set it up to a final set of conditions as well. In this case, P2 over T2. So if we take our K out, we find that P1 over T1 is always equal to P2 over T2. So how do we write down what this law states? If we increase the temperature of a gas, we thereby increase the kinetic energy from our kinetic molecular theory. This increase in kinetic energy increases the number of collisions that the gas has with the container. And as we've seen, if we increase the number of collisions, we increase the force, which also increases the pressure on the container. So let's apply this law to a problem. Let's say we start with an initial pressure of 2 atmospheres, and that gas that's held in a container has an initial temperature of 25 degrees centigrade. The first thing we need to do is convert that temperature to Kelvin. So to do that, we get the 25 plus 273, which gives us 298 Kelvin. We're also told that our final pressure is 5 atmospheres. And we want to know what's the final temperature when this gas goes from our initial conditions to our final conditions. So we set up our equation, P1 over T1, which is our initial set of conditions, equals P2 over T2, our final conditions. Now to rearrange this equation, we need to do 3 things. First of all, we multiply both sides by T2 to get rid of it from the bottom here. We'll then divide both sides by P1 to get rid of this term here, and then we'll multiply by T1 to get rid of T1 over this side. And that then isolates T2 on the left-hand side for us. So T2 is equal to P2 times T1 all over P1. So if we put in our numbers, we've got 5 atmospheres as our P2 times our 298, we must have it in Kelvin, divided by our 2 atmospheres. And if we do this calculation, we've got atmospheres on the top, atmospheres on the bottom, we end up with 745 Kelvin. If we convert that back to degrees centigrade, so we have to subtract 273, we get 472 degrees centigrade. So we always ask the question, does this answer make sense? Well, let's look at it. We're going from 2 atmospheres to 5, so we're increasing the pressure by a factor of 2.5. Therefore, our temperature should go up by that factor as well. So we're going from 298 to 745, which if we did a quick calculation, we would find that that has indeed increased by a factor of 2.5. So this number does make sense to us.